Introduction. Now, as I said, I'm going to present a work that we've published by the beginning of this year in Scientific Reports, and it is called Evaluating Variant Calling Tools for Non-Matched Next-Generation Sequencing Data. Now, what was our motivation actually for this work? As you all know, there is, of course, an increasing importance of NGS, and this is not only true when you consider research, but also in clinical use case, so personalized medicine. And what you do, of course, need are valid results. So you have a real need for high sensitivity and high positive predictive value in results. However, when you start looking for variant calling tools, you will quickly observe that there are actually plenty of tools performing this calling step. And well, even when you go for what we think should be the simplest thing, so SNV and small indel calling, there's so many freely available tools, and they all have various algorithms they're using. And while some are performing partly local realignment to improve the indel calling, while other tools are completely ignoring this option. And all of these tools, they're reporting so many different parameters, and then they recommend filtration on the basis of these parameters. And of course, all the tools claim to be the best and the perfect solution for the variant calling problem. But actually, why are there then so many tools? And so the question that is, of course, arising from this observation is the one solution already available upon these tools, or maybe not? So what we did was actually looking everywhere we could basically think of. So we did a PubMed research, and of course also looking at Google, and we looked for just variant calling tools, everything we could find. It's displayed on this screen, and I hope I did not overlook too many. There are 45 tools, and we had to look at each and every one of these. And unfortunately, we had to exclude quite a few of them afterwards because they did not match our data in most cases. They relied on matched data only, so you would need tumor and germline samples. But we only had tumor samples. Okay, so we had to exclude them. There were other cases where the download links were not working, where the installation scripts were failing, and so on. But in the end, we came down to a list of 8 tools that we could really study in detail on the basis of our data. And these are Freebase, GTK's haplotype caller, LowFrag, Platypus SAM tools, SMVR, VarDict, and VarScan. Now, what's the data we analyzed? We're fortunate to have real data, and they're really well characterized. They all result from MDS patients, which is myelodysplastic syndrome, and we had a high-seq and an X-seq data set. And, well, obviously they differed in the sequencing technique, but also in some of the other characteristics. So yes, you can see there are different sample sizes, different background noise, different coverage. But what they really share, what they had in common, and was very good for our analysis, was a common target region of more than 42,000 base pairs. So we can perform variant calling and directly compare our results for these samples. Now, I said they are well-characterized data sets. We performed a lot of validation experiments. We had Sangus sequencing, we had resequencing on the same platform, resequencing on another platform, expert-based review. I can tell you it was quite a lot of work, but we had to look at each and every call in the IGV. And then we came down to a set of ground truth. But of course, you can never be 100% sure that this is actually the biological truth. And this is where simulated data gets really attractive. And this is also what we did. We simulated additional data. And actually, we tried to make it as similar as possible as real data. So we had our high-seq and our simulated next-seq data. We chose exactly the same coverage as we observed in the real data. And then where we used art for simulation, and this has the possibility of estimating base quality profiles and using this for simulating the error rate. So we did this, we simulated the same error rate as in the original data. Yeah, and that should actually match our real data. And then we also started playing around a little. So we increased and decreased coverage, we increased and decreased the error rate, just to investigate what is the effect on our variant calling process. And to each and every one of the samples, we randomly added common polymorphisms and common hotspot mutations using BAM surgeon. Now, what did we do for our analysis? Well, of course, at first you have our read alignment, we have BWMM for that, then you have the variant calling process for the 8 tools. We excluded quite a few calls that we were not interested in this case, so were all off-target calls, calls in the non-coding region, silent mutations. We determined a basic set of characteristics for the coverage and for the allelic frequency, and we removed all calls with insufficient coverage and very low allelic frequency, so anything below 1%. And then for the remaining set of calls, we determined a more elaborate set of characteristics, and this considers mean base qualities. We had an automatic checkup of various databases, and we considered the influence on the protein. And then we combined all of this information for each and every call, and we performed a variant classification together in close collaboration with independent biologist. And so we came down to a list of polymorphisms, true pathogenic mutations, and artifacts. So I think now we can go for the variant calling results. Most interesting, I think, are these for the real data. These are quite a lot of numbers, but I just want to draw your attention to very few of them. When you go for the left part of the table, so the ISCB data, you can quickly see that from all 8 tools, only Freebase was actually able to call all the 113 variants present in the dataset, and this was quite alarming for us. LowFrag and VarDig, they're also quite good, but all the other tools actually show really problem in calling variants there. However, when you go for the artifacts then, you will quickly see that Freebase, our good sensitivity tool, was so bad at PPV. So it would, for a clinical use case, mean you have roughly 8,000 variants, and you're about, well, you have to identify roughly 102 calls in it, and this is just no way scenario. So when you combine both parameters, you will quickly see that VarDig is actually best with respect to sensitivity and PPV. However, then we analyzed our next data set, and things looked a bit different there. The best performance with respect to sensitivity was, well, VarDig. You can see it's 0.91, but still it misses 21 true calls. And well, all the other tools, they perform considerably worse. They're missing so many mutations, and they call even more artifacts in this case. So somehow this data set is much more complicated for variant calling. And after all, these results were really alarming for us. So we were asking ourselves the question, why is it? Why do we observe these big differences, not only between the data sets, but also between the different variant callers? So what you, of course, assume is that variant calling gets much more difficult when you lower the allelic frequencies. So we analyzed the relation between the performance of the tools and the allelic frequency, and we could find out that actually only Freebase and VarDig were really good at calls with 1% or slightly above, but LowFrag and Platypus only start being really good at variant calling at 10% or above. For GTK, it was a bit difficult. It was really good at 20% or higher allelic frequencies, and only partly it worked for, well, 5 to 20%. However, samples and VarScan, we would really not advise to use for the detection of variants below 20%, because we could see that it, well, you could basically not see anything. It hardly calls any variant at these frequencies. SMVR was also a very difficult case because its performance was so highly data dependent that we could not define any secure threshold for its usage. Now, when you go for the PPV, you, of course, expect to see low PPVs when you go for low-frequency variants, and this is what we also could observe. The only exception, and was very special case, was VarDig and SNVR in case of the Illumina HiSig data. So when you're using these tools, okay, maybe you're a lucky one, and you got also one of these special cases, have a high PPV, but you cannot rely on this. However, we could observe what we also expected was a data-dependent increase in PPV as the allelic frequency also increased. Now, what is still an unanswered question is, why do we observe such a big difference between our HiSig and our NextSig data set? And this is where we had a look at our simulated data, because we thought maybe it has got something to do with the differences in coverage or in the background noise. So what we did first was comparing our real data set with a matching simulated data set. And what you can see here is, well, the framed symbols that correspond to the real data and the unframed ones to the simulated data. And, well, actually the details are not that important, but what you can see in the plots is that you can see all kinds of symbols, and this is not really good, because when the data was actually matching, you would not only see one kind of symbols. But this just means, okay, our simulated data differs really quite a lot from our real data, and overall you can see a shift to higher PPVs, and we think that this can be observed because our simulated data was somehow completely lacking systematic errors. Well, we had our data, so we still evaluated it, and we could find out that for variant coverage, there was hardly any influence on the variant calling process, and only in very few cases we could see that there was a decrease in sensitivity when coverage decreases. This was actually what we expected to see for all the tools, but we did not. Considering variant background noise, we could just see hardly any influence. Now, I've got a few more additional results for you, which I think could be very interesting. It seems obvious, but we also consider reproducibility. We took the same inputs, the same BAM files, the same analysis scripts for the pipelines, and we just restarted the pipeline. And of course, you would expect to get the same output. Unfortunately, you did not in 1 out of 8 tools. It was unfortunately VarDig. You have really many raw calls, and considering the high number of raw calls, it's only a minor deviation, but still you see differences. 8 calls were reported differently, so with different values of their characteristics, and we had 1 missing call. However, these 11 differences, they all consider indels, and we know from the VarI algorithm that the indel calling process consists of a non-deterministic step, and we think that this might be the cause for the observed differences. Things get a bit more interesting when we consider multi-threading mode, because 3 tools, they have a multi-threading mode, and we restarted our pipeline using 8 threads instead of 1, and 3 out of 3 tools have different results. Platypus is still best, just 2 different variants and 1 additional. However, for low-frag, we think that the tool has a bug, because in multi-threading mode, 2 filters, these are namely the SNV quality and the indel quality filter, they get analyzed twice, and it's reported twice in the header of the VCF file. And this finally leads to quite a few variants being missing, and also a few additional variants. However, well, in case of multi-threading, worst performance was unfortunately GATK, where we had 82.7% of the calls with different quality parameters. This was quite alarming, as GATK recommends filtration on the basis of these parameters. We have roughly 7.5% missing calls and almost 8.5% additional calls. And these numbers were roughly comparable for both data sets. So, additionally, we considered output comparability. You would expect to see somehow comparable output for all tools, but you did not. Not even all tools report VCF files. Some also have text files. Some have more than 1 file. There are different ways of reporting indels. Only 2 tools report MNVs. So in the end, only 3 tools report the output in the same way. So whenever you want to combine your data, you definitely need a post-processing step. We also had a look at runtime. For the real data, we could see that in the case of the high-sig data, Platypus was fastest, GATK was slowest, and for the next SIG data, SAMTools was fastest. That was incredible because it also had a pre-processing step, and SNVO was the slowest. Now, for the simulated data, it was very nice to see that an increase in coverage led to a very nice increase in runtime. The only exception were GATK and SNVO, which had a more extreme increase in runtime at very high coverage. So whenever you have ultra-deep sequencing data, this might be a problem. However, when we have an increase in background noise, there was hardly any influence. Only in case of GATK, Freebase, and VarI, we could see an increase in runtime. So, concluding, we can state that variant calling, even of SNVs and short indels, remains a very challenging topic, and the performance of every tool we analyzed was highly data dependent. In the end, no tool succeeds in calling all the variants we validated in our data sets, and based on the real and the simulated data, we would still advise the application of VarI, although it does not lead to perfect results. So I think you will all agree with me that these results are, after all, not too satisfying, and, well, I can tell you we were not too happy with it either. So we were asking ourselves the question, what can we do to improve this? And, well, we had quite a few ideas. So what we thought of was, okay, why don't we take a tool, the best tool, and we apply some cool, fancy, model-based filter to it. That would solve our PBV value problem, but we still have a problem with sensitivity, because a single tool would never lead to high enough sensitivity. So we need something better. So why don't we take several tools, and then we apply our cool, fancy model, our filter model. Yes, this is better, but it would be necessary to determine tool-independent parameters in this case, and we would need really large, appropriate training sets, and still there's always the risk of overfitting. Okay, so why don't we make it easier? Just take a selection of best tools, for example, Freebase and VarI, and for example, whenever they overlappingly report a call, just go for it, and then you believe in this. This could be a real call. Yes, we tested it. We actually tested each and every combination of 8 tools, and whenever we found a combination that was really good on one data set, and we tested it on the other data set, it completely failed. So in this case, it was highly data-dependent performance, and we really would not go for this solution. So this is why we came to our final solution. Just take all tools. We have information from 8 tools, so just combine it. Take it all, and then apply some comprehensible filter, something that seems logical. And this is how we developed our tool. It's called Appreciate, a pipeline for precise variant calling integrating 8 tools. And if I got 2 more minutes, maybe I would just quickly show you what Appreciate is doing and what it can do already. First of all, there's, of course, the variant calling with the 8 tools, and currently we can go for an allelic frequency of 1%. And there follow quite a few steps of normalization, combination, and basic filtration, and then we have a huge step of parameter determination. So each and every call is characterized by a lot of parameters. And then there's this comprehensible filtration step. So for every call, we determine an artifact score and a polymorphism score. And depending on how high or low this score is, our pipeline automatically classifies a variant, either as an artifact or a polymorphism or a likely pathogenic mutation. Now, we trained our pipeline, and hopefully you will recognize these two data sets because they're the one I talked about all the time now. They're HiSig and the NextSig data, and it's just important to see all the symbols down there and here, and these are the individual tools. And then it's important to see the black dot in the upper right corner. This is actually Appreciate, our pipeline, and you can see it has really high sensitivity and nearly perfect positive predictive value, and it clearly outperforms all the individual tools. Okay, it's just training set. However, when you go for a test set, and we had an independent Illumina HiSig data set, quite big, it looks quite similar. All the individual tools, they're roughly the same positions, but our Appreciate pipeline is still in the upper right corner. And then we even tested it on Roche 454 data, something that should be characterized by a completely different error profile. And yes, Appreciate is not perfect in case of this data set, so sensitivity is good, PPV could be better, but still, it outperforms all the other tools. So, I can tell you right now, we have analyzed more data. We had Illumina HiSig, MySig, and NextSig data, even iTorrent data. We considered different disease entities, so not all MDS. We had considerably larger and different target regions, and still it worked really well. Having said that, I'm reaching my last slide. I would like to thank you all for your attention. I hope you appreciated my talk. If you have any questions, maybe regarding our evaluation or interested in our algorithm or even data to analyze, just come and visit me at my poster. This is B331. I'll be there this evening. Or if you cannot make it, just send me an email. And if you're interested, don't forget to check out our pipeline, which is already available via Docker. Thank you.
Time for one quick question, if there is.
Thanks for the talk. So when you do this reproducible test, have you checked on those different variants, whether they are biased to some low-frequency variants?
Excuse me?
When you check this reproducible, so you run
Yes,
run variant caller several times and see what the difference. So whether those the variance difference is biased to some low-frequency variants or some
well, in
other
case
bias?
of GATK, the missing and the additional variants, they usually have very low frequencies. And I have to say, we also posted it to the forum that we observed these differences. And the comment was that is actually only considering so-called borderline variants, so these which are not likely to be true anyways. But it's not all low frequency. Sometimes it was also higher frequency. So I think it was really alarming that some of them are missed and only sometimes reported.
Okay, thanks.
Last quick question.
Yeah, thank you very much for the presentation. I think it's a very important topic. I would like to pose the question if you observed any change of the results when you altered the parameters, as for instance, the ploidy. The caller you showed, to my knowledge, are germline callers, which expect that you set a certain ploidy. And if you now add an allelic fraction, which does not match or correlate to that ploidy, as for instance, when you say ploidy 2, it would expect, usually because the germline callers, not somatic callers, that don't have that ploidy setting in general. It couldn't work because, just to my understanding, if you set it to diploid and you add an allelic fraction which does not match that, then it's kind of what the callers should do, not to pick up that because you set it to diploid. Did you observe that? Did that make a difference?
Actually, for the tools, we mainly stick just to the default options because all the tools, there's such a large list of options, and you could just not change everything to observe all the difference. So we mainly stick to the default options and just sticking to the what they recommended to achieve the best sensitivity at all. So we just decided to go for this, and we only lowered the allelic frequency threshold and just make it as sensitive as possible. So in the first round, we really tried to call everything with the tools as possible, and so still some missed quite a few calls. But yeah, that's a good point.
Okay, thank you again, Sarah.
Thank you.